Hi, and welcome to this first video on the topic of electromagnetic waves. Electromagnetic waves, or EM waves for short, are transverse waves that, like all waves, transfer energy from one place to another. In the waves which we've looked at up to this point, the things that were doing the vibrating were air particles or water molecules or bits of metal in a slinky spring, but in an EM wave, the vibrations come in the form of electric and magnetic fields which oscillate at 90 degrees to the direction in which the wave is travelling. Here, we can see that both the electric and magnetic fields of an EM wave are perpendicular to the direction of wave motion. As you can also see, the electric and magnetic fields are at right angles to one another as well. Electromagnetic waves form a continuous spectrum, which means that they can have any wavelength and frequency. We normally group EM waves into one of 7 types though, and you'll need to remember their names and their order for the exam. Going from the shortest to the longest wavelength EM waves, we have gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. All 7 types of EM waves have a number of things in common. As we've already said, they're all transverse waves which transfer energy from one place to another. They can also travel through a vacuum. If they couldn't, we wouldn't receive any of the sun's energy on Earth. And they travel at the same speed in a vacuum, 3 × 10 to the power of 8 meters per second, or 300 million meters per second, the speed of light in vacuum. Thinking back to the wave equation, V equals F lambda, we can see that the frequency of a wave is given by F equals V over lambda. In other words, the frequency of a wave of constant velocity is inversely proportional to its wavelength. What this means is that the shortest wavelength EM waves have the highest frequencies, and the longest wavelength ones have the lowest frequencies. In our next video, we'll learn about each of the 7 types of EM wave in detail, but for now, we're going to concentrate on more of the things which all EM waves have in common. All EM waves can be reflected when they arrive at a boundary between one substance and another. Have a look at this light ray as it's reflected by a mirror. We can draw a normal at the point at which it strikes the mirror. A normal is an imaginary line which is drawn at right angles or perpendicular to a surface. The angle between the normal and the incident ray, that's just the ray that's travelling towards the surface, is called the angle of incidence, I. And the angle between the normal and the reflected ray is called the angle of reflection, R. No matter what type of wave we're dealing with, and whatever the surface, the angle of incidence is always equal to the angle of reflection. This statement is called the law of reflection. An EM wave won't always be reflected from a surface, however, and whether or not it is depends on its wavelength. So far, we've seen that when an EM wave travels from one medium into another, it can be reflected at the surface. It can also travel into and be absorbed by the object, or it can be transmitted right through the object and come out the other end. The amount of wave energy reflected, absorbed, or transmitted depends on the media which the wave is travelling through, the distance travelled by the wave. Here, for example, the thicker the block, the greater the amount of wave energy absorbed inside it, and the less energy that will be transmitted to the other side. And finally, the wavelength of the wave. Let's look at what this all means for visible light. The colour of an object depends on the amount by which different wavelengths of light are reflected and absorbed by its surface. When illuminated with white light, for example, a green plant appears green because it reflects green light really well and absorbs the other colours in the visible spectrum. A full moon appears white because it reflects all of the visible wavelengths, or colours, that make up the sunlight that's striking it. And when we wear sunglasses, a lot of the light waves that strike their surfaces are either reflected or absorbed by the glasses, which decreases the amount of light transmitted through to our eyes and makes it easier to see in bright conditions. If they're proper sunglasses, they should also prevent potentially harmful ultraviolet rays from reaching our eyes. Here are a couple of other examples. In a microwave oven, the microwaves are absorbed by water molecules in your food. This transfer of energy from the microwaves to your food is what increases its temperature and causes it to cook. Radio waves, microwaves, infrared, visible light, and ultraviolet will all be reflected by a standard mirror, but X-rays and gamma rays will pass straight through it. Have a look at this picture. Notice anything strange? Yep, it looks as though my lovely spoon is broken, But don't worry, no spoons were harmed in the making of this video. This optical illusion is caused by a process called refraction. Refraction is the change in direction of a wave as it travels from one medium into another. It happens when a wave changes speed upon travelling from the first medium into the second. Here, this light ray refracts towards the normal as it travels from air into glass. As before, the angle of incidence is the angle between the incident ray and the normal. The angle of refraction is the angle between the refracted ray and the normal. Be careful here because, as confusing as it is, the letter R is often used to represent both the angle of reflection and the angle of refraction. In this diagram, a ray of light is travelling from air into a glass block, then out the other side. Where the ray is travelling from air into glass, it refracts towards the normal because light travels more slowly in glass than in air. When the light travels from glass back into air, it refracts away from the normal because light travels more quickly in air than in glass. In general, when a wave of any type slows down upon travelling from one medium into another, it refracts towards the normal, and when it speeds up, it refracts away from the normal. The only time a wave won't refract on moving from one material into another and changing in speed is when it's incident onto the surface at right angles like this. This is often called normal incidence, where the angle of incidence is 0 degrees. The required practical for this part of the course is on investigating the reflection and refraction of light. Let's look at each of these in turn here. We already know that when a ray of light is reflected from a surface, its angle of incidence is equal to its angle of reflection, but how do we prove this experimentally? First, you have to use a stand to place an upright plane mirror onto a sheet of paper, then draw a line onto the page to mark the position of the mirror. We then direct a ray of light from a ray box towards the mirror and draw 2 points on the page here and 2 points here to mark the incident and reflected rays. Once you've removed the ray box and mirror from the page, you can draw the incident and reflected rays with a pencil and ruler. Then draw a dotted normal line before using a protractor to measure the angles of incidence and reflection. By repeating this process for a number of additional angles of incidence, you'll build up a full set of results. Typical data from this experiment might look something like this. We know from theory that the angle of reflection is always equal to the angle of incidence, but we can see here that this isn't the case for this data. This is because there'll always be a certain amount of random error in any experimental measurement. Random error is the name given to the unpredictable fluctuations which occur each time a measurement is repeated. Here, someone might measure an angle of reflection of 29 degrees the first time around, then decide that it's actually closer to 30 degrees following a second measurement. This could be caused, for example, by the fact that the ray of light is quite wide compared to a single division on the protractor. When we're writing down a numerical measurement, we often include its uncertainty. Rather than simply stating that an angle is 60 degrees, for example, we might say that it's 60 plus or minus 2 degrees, which means that we think it's 60 degrees, but it could be as low as 58 or as high as 62 degrees. The plus or minus 2 bit here is referred to as the uncertainty in the measurement. A graph of these results looks like this. We can see that it's a straight line of positive gradient which runs through the origin. Here's a different set of results from the same experiment, but if we draw a best fit line through the points in this graph, we can see that something strange is going on here. The best fit line doesn't go through the origin, and all of the angles of reflection are around 5 degrees too large. We say that there's a systematic error in these readings. A systematic error is one which is always too big or too small by the same amount. In this case, the experimenter may have been reading the protractor incorrectly in the same way each time, or perhaps the normal was drawn at an incorrect angle to the surface of the mirror, in other words at 85 degrees instead of 90 degrees to the surface. Now that you're light ray measuring experts, we can whiz through the refraction experiment which you need to know about for your exam. The equipment that you need is very similar to the previous reflection experiment, except that here we'll be using a glass block in place of a mirror. You start by directing a light ray through the block at an oblique angle like this. Use a pencil to draw around the block, and use 2 dots each to mark in the positions of the rays which are entering and exiting the block like this. You can then move the ray box and block to one side, before using a ruler to draw in these 2 rays. The ray which travelled through the block can then be marked in like so. Almost there now. By drawing in a dotted normal line at 90 degrees to the surface at the point at which the ray entered the block, like this, you'll be able to use a protractor to measure the angles of incidence and refraction. Once you've recorded these values in a table, you can repeat this process for a number of additional angles of incidence. Results from this experiment might look something like this. As you can see, this time, the relationship between the independent and dependent variables is not linear, with the best fit line curving noticeably at high angles of incidence. One last chart section now on wavefront diagrams. Here, we're looking at a water wave side on and can see all of its peaks and troughs in all their glory. To represent the same wave top down, we need to use a wavefront diagram like this. Here, each of the black lines represents one of the peaks of the wave above. Wavefront diagrams are useful because they allow us to see very easily whether the wavelength of a wave is getting shorter, longer, or staying the same. Although we can produce wavefront diagrams for an EM wave, it's nicer to use them to think about the refraction of water waves. Here, we're looking at what happens when these water waves are travelling from deep water into shallow water. Water waves travel more slowly in shallow water than in deep water. Like the boundary between the deep and shallow water, the wavefronts slow down, which causes them to refract towards the normal. This decrease in speed causes the wavefronts to bunch up. In other words, it decreases the wavelength of the wave. If waves were coming in from the shallow water region on the right instead, the opposite process would happen. They would speed up and entering the deep water, which would cause them to refract away from the normal and increase their wavelength. But as that's probably about as much fun as we can have in one video, we'll leave that diagram for one of the exam style questions. Thanks for watching and good luck.